Today, we're cracking open a scientific case file. It's a digital detective story that's going to take us from these massive computer simulations all the way down to the cellular level. And it's all in the hunt for a better way to treat a really serious and widespread condition. Our whole investigation, it kicks off with just one single, staggering number. Here it is, our first big clue. 200 million. That is the estimated number of women, just women, around the globe affected by osteoporosis. I mean, that's an incredible figure. It just shows you the sheer scale of the case we're diving into, a health challenge that really touches every corner of the world. But, behind that giant number is a very human cost. Osteoporosis is often called a silent condition, and for good reason. It weakens your bones over time with almost no symptoms. For a lot of people, the very first sign is a sudden, painful fracture, from something as simple as a minor fall or even a bump. And a break like that, it can totally change your quality of life. So the big question for scientists is pretty clear. How do we find safer, more effective ways to fight back against this? Well, the study we're breaking down today does exactly that. It's all about following the clues, using some really cutting-edge tools to zero in on a prime suspect. Okay, so let's start our investigation by really digging into the problem we're up against. We're talking about postmenopausal osteoporosis, or PMO for short. So PMO is the most common form of this condition. It's triggered after menopause, when there's a big drop in the hormone estrogen, and that drop just accelerates bone loss. It leaves your bones porous and brittle. Think of a honeycomb, but the holes are just getting bigger and bigger. That makes them incredibly vulnerable to breaking. All right, with the problem established, every good detective story needs a promising lead, right? And in our case, a new candidate has definitely emerged in the search for a better treatment. Now, it's not like we're starting from scratch here. There are treatments out there, like hormone replacement therapy, which helps bring that estrogen back. But the thing is, that can have some pretty broad, system-wide side effects. So the scientific community is always on the hunt for alternatives that can give you those bone-protecting benefits without all the risks. And this brings us to our main suspect, a compound called Ipriflavone. The central clue, and it's highlighted right here, is all about how it might work. See, early research suggested that Ipriflavone could interact with the body's estrogen receptors, the exact same ones that are involved in keeping our bones healthy. So the theory was, what if this thing could mimic the good stuff estrogen does for bones, but in a much more targeted and maybe, just maybe, a safer way? So to test this theory, the researchers didn't immediately head to a lab full of beakers and test tubes. Nope, they went digital. They launched this massive computational investigation to see if the evidence would even hold up in the first place. Okay, so the first step was to cross-reference two huge sets of data. They used these giant biological databases to pull a list of 171 genes that we know are involved in osteoporosis. Then they identified 201 potential gene targets for our suspect, Ipriflavone. And as you can see in this diagram, the big breakthrough was finding the genes that were on both lists, that critical overlap right in the middle. And right there, in that little intersection, they found their primary list of suspects. I mean, think about it. Out of hundreds of possibilities, the investigation narrowed its focus down to just 8 common gene targets that were linked to both the disease and the drug. That is a huge step. It takes this massive, complicated problem and makes it something you can actually work with. So next, they had to see how well their suspect fit the crime scene, but at a molecular level. For this, they used a super powerful computer simulation technique called molecular docking. And you can think of it, exactly like trying to find the perfect key for a specific lock. The drug, Ipriflavone, that's our key, and the target proteins on those 8 genes, those are the locks. A perfect fit means you get a really strong, effective interaction. And boom, here it is. This is the smoking gun from the digital investigation. The computer simulation showed that Ipriflavone bound most strongly to estrogen receptor 2 and estrogen receptor 1. Now, with these scores, the lower the number, the stronger the bond. That negative 8.7, that is a fantastic score. It's powerful computational evidence that backs up their original theory. This compound is going right for the estrogen receptors. So they found a key that seemed to fit the most important lock perfectly. But the next question is, would that connection actually hold up over time? To figure that out, they ran one last digital test, a molecular dynamic simulation. For 200 nanoseconds, which, trust me, is an eternity in the molecular world, they basically simulated how the drug and the receptor would behave together. They stress tested that bond to make sure it was stable, not just some fleeting connection. And you know what? It passed the test. Okay, so with a really compelling case built inside the computer, it was time to move this whole investigation into the real world. Time to hit the lab and see if these digital predictions actually hold up with living cells. So the lab work was really logical. It followed this simple two-step process. First, and this is the most important part, they had to confirm it was safe, right? I mean, you don't want a treatment that ends up harming the very cells you're trying to help. And then, second, they needed to see if it actually worked. Does it make bone cells do their job better? This first chart here shows the results for step 1, safety. They took human bone-building cells and exposed them to Ipriflavone. The bars you see on the chart, they represent how many cells survived. And as you can see, even at pretty high concentrations, the cells stayed healthy and viable. In fact, some even seemed to thrive. So, confirmed, it's non-toxic. First test passed with flying colors. And now for the big one. Does it actually work? This chart shows how much calcium the bone cells were able to absorb, and the result was an absolute home run. Just look at how as the dose of Ipriflavone went up, as you move from left to right on the chart, the cells absorbed way more calcium. This isn't a simulation anymore. This is direct biological proof that the compound is actively promoting bone-building activity. So, after following all the clues from these complex computer models all the way to the lab bench, what's the final verdict? Well, the evidence they collected paints a really clear and very, very promising picture. So let's just recap the case here. The digital investigation, it showed us that Ipriflavone strongly targets those key estrogen receptors. The computer simulations predicted that this connection would be stable and effective. Then, the lab work came in and confirmed it's safe for human bone-building cells. And then, the final piece of the puzzle. It proved that it actively helps those cells do their job by ramping up calcium uptake. When you put all that together, you get a really powerful body of evidence that points to Ipriflavone's huge potential as a new weapon against osteoporosis. But of course, in science, one study is never the final word. The researchers, and they're right to do this, conclude that the next big step is to move from the petri dish to living organisms, what they call in vivo studies. This is absolutely crucial to see if these amazing results hold true in a much, much more complex biological system, like in an animal model. But you have to admit, this digital detective story gives us an incredible roadmap. It really shows how modern science can intelligently and efficiently find and validate new treatment possibilities. And it leaves us with this one really compelling question. With a suspect this promising and evidence this strong, what will the next chapter of this investigation reveal on that long road from the lab all the way to the pharmacy?